Good morning dear students, welcome back. Today we are going to discuss about the magnetic field due to a current carrying solenoid. It's not due to a solenoid, it's due to a current carrying solenoid. So what is solenoid? You are hearing this for the first time. Maybe you are hearing it for the first time. So let us discuss what is solenoid. For that let me take this duster. So I have a wire with me. Simply a wire that is wounded or winded on a cylindrical cardboard as like this. A wire simply wounded on a cylindrical cardboard. This is just solenoid. One condition is that its length should be greater than its diameter. If it is a cylinder, this will be its diameter. Diameter should be lesser than the length, or length should be greater than the diameter. That is the condition. So this is a solenoid. Its length is this much is the length of the solenoid. It's greater than the diameter, hence this is a solenoid. It must be wounded on a cylindrical cardboard or cylindrical surface. So such type of a connection or figure is known as solenoid. So we know that whenever the current passes through any of the object, there will be a magnetic field connected to that object, isn't it? Therefore, when the current passes through the solenoid also, there will be a magnetic field. We are going to study the pattern of magnetic field due to a solenoid. For that, we made an experimental setup. Here is a battery terminal with positive and negatives. Here is a rheostat, here is a key. So these are connected to a solenoid. So here from the positive side the current flows through the negative side, isn't it? That is the direction of current flow. Hence the current is flowing through the inner surface and coming back, and it's going like this, and at last is going to that end and coming back to the negative terminal. So it is as like, see, it's entering from the back side. So it's like this. Okay. It's actually like this one. Hope you can see this figure. See, this is solenoid. The current is entering like this and it's going like this. See, it's a clockwise direction, isn't it? Clockwise motion. See, the current is flowing like this. That is a clockwise direction, and at last it is coming back through this section. The current is entering and going back. It's entering to the back side as like this, entering to the back side and going. So it's a clockwise direction. So what happens when it is clockwise? When the current flows in the clockwise direction, that indicates which pole? Already we studied in the case of circular coil. That indicates the south pole. And if the current goes in the anti-clockwise direction, it indicates the north pole. Obviously, if one of them end is south, the other end will be north. For which thing we have south and north? For a bar magnet, isn't it? For a bar magnet, we have north and south. As like a bar magnet, this solenoid acts. So this acts as a bar magnet. So it can do any functions as a bar magnet too. Bar magnet can attract the things. It will, when it is hanged freely, when it is freely suspended in air, the bar magnet will lie in the north-south direction. As like that, this solenoid also, when the current is passing through them, it will act as a bar magnet and it will align in the north-south directions. And also it have the attractive property as like the bar magnet. So when we pass the current in this experimental setup, we place a compass here, compass needle here, inside the solenoid. We found that inside the solenoid, magnetic field lines are straight and parallel. Straight and parallel magnetic field indicates uniform magnetic field. So that is the first point. Magnetic field inside the solenoid is found to be uniform. And second point, it behaves like a bar magnet. So bar magnets have attractive property and directive property. Both the properties are shown by this solenoid also. it have attractive property. It will attract the objects, and also when it is freely suspended in air, that is when it is hanged, it will lie in the north-south direction. That's why we can say it acts as a temporary magnet, temporary bar magnet. See here, as in the case of bar magnet, here this one also have this closed magnetic field lines. The magnetic field lines are found to be closed and continuous, and is the same as in the case of bar magnet, isn't it? Inside the magnet, the direction was from south to north, and outside the magnet, the direction was from north to south. So this one, magnetic field lines are arranged as like they are directed from north to south direction. They are closed and continuous curves as in the case of bar magnet too. So these are the properties. Inside the solenoid, the magnetic fields are found to be uniform. It behaves like a bar magnet. It aligns in the north-south direction, and it shows the attractive property. Now let us check the magnitude of this magnetic field. Already we got the direction of magnetic field. How? According to the clockwise and anti-clockwise directions, anti-clockwise movement of current, we got the direction of magnet, south pole and north pole. If it is clockwise, it indicates the south pole. If it is anti-clockwise, it indicates the north pole. Now moving into the, one second. Yes, now moving into the magnitude of a magnetic field. Magnitude of magnetic field due to a solenoid, current carrying solenoid. We know the letter indicating the magnitude is B. We found that when current is increased, obviously the magnetic field strength are found to be increased. So we can write B is directly proportional to I. What happens if current is increased? How we increase the current? Decreasing the resistance. So if the current is increased, we found that magnetic field, magnitude of magnetic field also increases. B directly proportional to I. Second one, when we increase the number of turns per unit length, we have one condition, number of turns per unit length. That's not the number of turns as we discussed in the earlier case. Number of turns per unit length. What it means is, suppose this solenoid have 50 turns, and its length is 2 meter. Then what is the number of turns per unit length? Number of turns per unit length is 50 by 2, that is 25 turns per unit length per meter. 25 turns per meter, that is the number of turns per meter. It is 50 turns for 2 meter. The number of turns of this solenoid is 25 meter. How we get that? Dividing the turns by length. So I have another solenoid. Suppose I have another solenoid with 60 turns and its length is 6 meter. Suppose its length is 6 meter. Obviously, when we see firstly, it have 50 turns and second one have 60 turns. That is 60 turns. Which will have more which will have more strength? We will go for 60. But actually, what we have to do? We have to divide it by the length. So this is only 10 turns. 10 number of turns is only 10. 60 divided by 6 gives 10. Here it is 25. Per meter is 25, is 10 per meter. So which solenoid will have more strength? This one will have more strength because number of turns per unit length is greater for this one. So we have to remember its number of turns per unit length. So combining these two, we can write B proportional to Ni. So this is the required equation, that is the magnitude of magnetic field, B proportional to Ni. And that's all about this section. So once again, we discussed the magnetic field due to a solenoid. First thing we discussed is what is a solenoid. Then second thing, what happens to the current when the current enters into a solenoid. By using an experimental setup, we pass current through the solenoid, and we find that it produces a magnetic field as like in the case of a bar magnet. And inside the solenoid, the field lines are found to be straight and parallel. Therefore, the magnetic field is uniform inside the solenoid. Second point, according to the direction of current, we found the poles of a magnet, and we found that it almost acts as a bar magnet because it shows the attractive property and it shows the directive property. It attracts the objects and also it aligns in the north-south direction when it is hanged or suspended freely. Then the point to remember is the direction of magnetic field, that is the north pole and south pole we got by looking into the direction of current flow. If it is in the clockwise direction, it indicates the south pole, anti-clockwise direction indicates the north pole. And last point, magnitude of magnetic field. It is found that when the current is increased, magnitude is increased. If number of turns per unit length is increased, then also magnitude is increased. So combining these two, we can write B proportional to, combining equations 1 and 2, we write B proportional to Ni, where you have to write every time where N equal to number of turns per unit length and I is equal to the current flow through the solenoid. Current flowing through the solenoid. Okay, that's all about this section. Hope you understood. Thank you for watching.